So yesterday we started discussing about various architectures of adders, which is the only way in which you can speed up the performance of an adder, right? Beyond the point, you can do circuit techniques to speed up a little bit, but beyond the point, the ripple delay, right, is T sum plus n minus 1 T carry, right? And if this is the case, then the delay is determined primarily by n. So it doesn't matter how much you can decrease T sum and T carry at a circuit level. So you're limited by n, and therefore you have to start thinking of various architectures of ripple adders. And in that pursuit, we discussed the first adder called the carry skip adder. Right? And the idea of a carry skip adder was to simply bypass the carry, bypass all the full adders in a single stage if all the propagates are 1. So we basically said that we'll put a select line here called P0, P1, P2, P3. Right? This select line is basically product 4 to 7 pk. Right? Like that, you just put a multiplexer, and the worst case delay, which is the case when all the adders are in propagate mode, you bypass through the multiplexer. Right? So with this, what we were able to do is the critical path, right? Actually, this blue line is slightly wrong. It has to go through the carry propagation. It has to be like this, right? So you do a generation of G and P terms for all the adders in time TGP, right? And then you propagate through the first stage. However, in the first stage, you don't have to wait for the sum to be ready. So you just have to allow the carries to propagate through that. So which means that the first adder has to be in generate, the remaining have to be in propagate mode. Right? Similarly, but after that, everything has to be in propagate mode. Correct? And therefore, we got the expression for the carry skip adder as what? TGP plus M times T carry. Now you have to bypass n by m minus 1 multiplexers. Right? So if this delay here, the multiplexer delay is shown here as T bypass, right? Then you have to do n by m minus 1 T bypass. Why n by m minus 1? Because if this stage also is going to bypass, then the carry will be ready. However, that does not mean that the sum is ready. Ultimately, we want all the sum bits and the carry out bit to be ready. Only then our computation is done, right? So therefore, the last stage cannot be in bypass mode, right? So this is going to be in bypass, right? This will be in bypass. But this is not going to be in the bypass mode. I mean, that is not the delay. It can be in bypass mode. But we have to now consider the delay going into the sum here. Okay? Or in fact, I need to draw this on that side. Propagate and then bring it out here. Right? So therefore, we said that the last stage is going to be what? M minus 1 T carry plus T sum. Okay? So now how does this compare, this delay term, how does it compare with the ripple adder term, right? Clearly what we have done is, wherever there was n, we have brought that down to n by m. So clearly there is some saving, right? But definitely and quite obviously, it cannot give you savings if you have very few bits, because now I have actually added a multiplexer in the critical path. The ripple adder did not have that multiplexer. Now I have put a multiplexer. So it is bound to give you larger delay if there are fewer bits. But as you go higher, looks like beyond about 4 bits or so, the carry skip adder starts giving you good advantage. Okay, this is what is shown here. Ripple adder is basically the line in red, right? It starts off with lower delay up to about 4 bits, somewhere around 4 bits. Then up to 4 bits, the carry skip adder has slightly higher delay. Beyond that, the carry skip adder starts having better delay than the ripple adder. Okay. So, in summary, we are still limited by the rippling. Okay. Though we have brought it down to n by m. Okay. So, let's see how we can improve on this further. Okay. So, now you have, let me get the name right. I keep forgetting this name. Carry select adder. Yeah. So, we're going to do a carry select adder. So, in the last stage of this carry skip adder, right here, we had to wait for the carry to actually ripple through and then produce the sum outputs. Can we do better than that? Right? Can we avoid that rippling? Is the question. Okay? So, if that were the case, how would we do it? So, the point is very simple. The carry in that is going to come to this final stage here, this C in, right, is going to be either 0 or 1. Right? It's a bit. Therefore, you double the hardware and evaluate the sum and carry for both C in equal to 0 and C in equal to 1 and keep it ready. The aim here is to improve performance. My power can go up, my area can go up. There is no problem. If area goes up, power will go up. Because width goes up and therefore capacitance goes up, dynamic power C VDD square will go up. Right? But it's okay. Ultimately, I want performance. So the idea is, instead of just bypassing, you make a full adder, a ripple adder in that each block, right? And this is a full adder. Carry in will be grounded in one stage. This will go like this. Then I have another full adder, right? Maybe I should put it like this. Here you connect it to VDD. And then, as usual, I'm going to put a mux. What's my select line? C in of this stage. This is 0, this is 1. You'll get the C out. Right? Now, I also have to multiplex here and get my sum. S0. S1. S2 and S3. So now I've significantly increased the hardware. I've doubled the number of full adders. I've also added more multiplexers, right? But the advantage is that stage can actually evaluate that bit and be ready upfront. Okay? So now we are going to use this and construct the thing there. So in the interest of time, let me just sort of yeah. Okay. So as usual, we have a computing the G and P block first, right? So this is going to give you, or let me use blue there. The delay here is as usual TGP. Then it goes to the full adder rippling block that does evaluation of carry in equal to 0. In parallel, there is another block which does evaluation when carry in is equal to 1. Then I am going to send it through a multiplexer and the carry out will go. The sum, of course, will have its own multiplexer and all that. Okay? Right? So now, what is the first, what mode of operation should each of these full adders be in? Sorry? It can be? Okay, it can, technically it can be anything because we are evaluating this for both cases, right? So what is the critical path delay now, right? T select. Obviously, it has to take a time, TGP, of course, this is in parallel. Right? So this is TGP plus, what about the first stage? Do you have to wait for it to ripple through that or not? Huh? See, till now, up to this point, we have only generated the GP signals. We have created GP signals and only one small amount of time has elapsed. In that time, do you think this ripple adder could have rippled through already? No, right? So, technically, you have to have that rippling thing to go through. Correct? So, I expect, we will check. Okay, let's just write it this thing and then we will go back and see if the expression matches. If not, we'll see why. M times T carry. Right? Now, how many multiplexers do I have to bypass? At least n by m minus 1, like the last case. Right? Only thing is, what about that last multiplexer? Correct. So, this is actually n by m minus 1 T bypass of carry. But this sum now you need to multiplex. right? You have to put a multiplexer there and get the sum output also multiplexed, right? Which means if this block, if you see, there is actually a similar 2:1 bypass mux here that is going to select between the sums. So this will be S12, right? And this is going to come from the 0 block, S12 of 0, S12 of 1. It's going to, so therefore this bypass is plus T bypass or T mux of sum. Just to differentiate between bypass and sum multiplexer, I will write it like this. Of course, if all this is the same, then I expect it to be TGP plus MT carry plus N by M into T bypass. Is this expression right? So we can go and check if, if I made a mistake. N by M T mux plus there is a T sum. Okay. Okay, this is interesting. So now it depends on what this full adder block is. Okay. If my aim is to only propagate the carry, right, in this particular block, if my aim is to propagate the carry, then what I will do is I will not put a full adder here. I'll only put the carry out circuit of the full adder there. Correct? Because this path, along this path, we are only trying to propagate the carry. The sum can be evaluated in parallel. Correct? So here I will call it FAC, which means it has only the carry out part. What I'll do is, instead of this whole multiplexer thing, you're going to get the carry out, right? I can again multiplex, get the actual carry out here, right? And then I'll create the sum block. Right? You remember when we made the full adder circuit at a transistor level, we used the carry out to create the sum. You can now split that block. You don't have to put that entire, because remember now you're doubling hardware. So you double only the necessary hardware. So here this sum block, I am removing and I have only one per full adder set. Right? So I have reduced the hardware here, but of course the sorry, right, the sum will then get created here, S0, S1 and so on. So that's why after you bypass, right, what has happened is this T by N, the last bypass is actually through this multiplexer. Then I have to create the sum, right? I have that thing to create, and therefore I will add one more term to this called plus T sum. Okay.